Okay, all right. Good morning. Uh, Thanks for coming. So, as promised, the plan is to uh, the plan is for me to present our recent work on this weighted K-server problem on uniform metrics. But in case you have forgotten, here is a quick recap. Uh, we have this is basically a weighted version of the paging problem where you have sort of slow memory having several pages, you have a cache, and the cost of replacing a page within the cache is different for each cache location. Now, rest of the setup is the same as the usual paging problem. You get a request to a page. If that page is not in your cache, you have to replace some page in the cache by the requested page, and in this process you pay an amount which is equal to the weight of the cache location. Okay, so I'll use cache locations and servers interchangeably. I hope you have the context from yesterday. So the plan is to present this result of ours, which will appear in SODA this year. So the claim is that there is an exponential k-squared competitive algorithm for the weighted k-server problem on uniform metrics. What does this mean? It means that there is this algorithm which guarantees that for every input, the expected cost of the algorithm is at most exponential k-squared times the optimum cost to serve that input. And remember from yesterday that I mentioned it is impossible to get anything better than exponential in k for this problem. Okay, so what is the plan for today? Well, what I'll do is I'll first present a deterministic algorithm for two servers, which means you have just two cache locations, replacement cost being W1 and W2. Then I will convert it into a randomized algorithm. And then I will show how do we extend it to k servers. And then I'll conclude with open problems. Along the way, we'll take two detours and also see some two classical online problems, the ski rental problem, which I'll call the umbrella rental problem since we are in Mumbai, and the hiring problem. Okay, so let's start with the first detour and jump to the umbrella rental problem. So the setup is the following: monsoon is around the corner. We have a choice to make. We can either rent an umbrella by paying ₹1 of rent every day, okay, or we have an option to buy the umbrella for some price B, which is much greater than 1, let's say. Uh, or what we could do is we could just rent an umbrella for the first few days. We'll have to figure out how many and then buy it. Obviously, we want to pay as little as possible. So let's say the monsoon lasts for some D days. If we knew the value of D, if we knew how long the monsoon is going to last, then it's obvious to rent the umbrella if D is less than B. Otherwise, you just buy it. Okay. But if D is unknown, what could we do? Well, what we could do is we'll just rent the umbrella until for the first B days and then buy it. Okay. So this will ensure that the cost that we pay is going to be okay. Yeah, it's going to be D if D is less than or equal to B, because we'll rent the umbrella in this case for the D days. Otherwise, we'll rent the umbrella for D days and buy it. So we'll pay a total cost of D plus B. And in any case, we are going to be at most 2 factor away from the optimum cost. Okay, so this is a very high level idea that we use in fact in our algorithm, right? So let's come back to the weighted 2 server problem. So you have 2 servers, 2 locations in your cache. Let's say the replacement costs are W1 and W2, and let's say W1 is less than W2. Okay, it is instructive to imagine that W2 is much greater than W1. Okay, so what we'll do is, just like we analyzed the LRU algorithm in yesterday's talk, we are going to divide this request sequence into several phases, and in every phase we'll ensure that the algorithm pays at most so much times the optimum cost for that phase. Okay, so how do we define a phase? Well, in our algorithm we are going to repeat a loop, and every repetition of every iteration of that loop will correspond to a phase. So what do we do? Inspired from the umbrella rental problem, we just pretend initially that we don't have the heavy server at all. We just serve all the requests using the light server. Okay, until what? Until we pay the total cost of W2, which is the weight of the heavy server. Okay, so there we used rented the umbrella to figure out whether it is good to buy the umbrella or not, right? Here we are basically using this part called the explore part to figure out what is a good location to put my heavy server on. Okay, so what page should I have in my heavy server, in my heavy location of the cache, right? So from the first so many requests, we'll figure out the most the D costliest requests, right? So every point in the metric space is going to result in some kind of a cost, the cost that we pay to serve requests to that point, right? So the question is, what are the D most costliest points? Right, so here D is a parameter to the algorithm. In this example, I have picked D equal to 3 arbitrarily. Yeah. Okay, so for every distinct page in the main memory, we'll keep track of how much have we paid to serve requests to that page, right? Obviously, if you have, so the number of requests is not the right metric, because if you have some 10 requests to the same page, you're only really paying for the first one out of them. Yeah. Mm-hmm. Mm-hmm. Cheaper server. Yeah. Yeah. What do you mean by cost? Because every time you are paying W1, yeah. But then how many? So you could have paid several times for the same request, right? So you just count how many times? Yeah, times W1. That's the cost you have paid. Exactly. Right. So now, once we have figured out the D most costly points, right, what do? Well, we start the second part of the phase called the exploit part. And in this exploit part, for each point in the set S, we do the following. We send the heavy server to that point P. Okay. And then we continue. We just stick to keeping our server at point P, and then we serve requests until we incur another cost of W2. Okay. And so on. So this happens for every point in the set S. Okay. So how much? So and once we are done with all these iterations, our phase is over. So how much are we paying for every phase? So it's a simple calculation, right? So in the explore part, we are paying a cost of W2. That's only by the movement of the light server. In the exploit part, we are moving the heavy server D times, because we are shifting from the red page, then to the green page, then to the blue page. Yeah, so that costs us D times W2. And between each of these, or rather after each of these movements, we are spending a cost of W2 on the light server. Right, so total cost is going in the phase is going to be like 2D plus 1 times W2. Yeah. Why the server cost so during this phase, how many times necessarily the server moves? Equal to the size of S. No, never more than. Never more than that. You are only going to visit exactly the pages that are in the set S. You show up, you always move the server. You just move the server over there and then continue. Right? That's more like a conservative calculation. Yeah. Sorry? Just one heavy server. No, so you move to the red point, you serve requests until you pay another additional W2, then you move to the green point, and so on. So this order doesn't matter. Let in an arbitrary order for now, let's say. Okay. So now let's try to bound the optimum cost in this case, right? So the question that we are going to ask is, what is the heavy server of the optimum doing? Okay, it could do lots of things. Case 1, if in this duration a heavy server moves at least once, right? So the optimum must pay a cost of at least W2 for moving the heavy server, right? So the hope is to prove that the optimum must pay about W2 in any case, no matter what. Okay. So in the other case, let's say so this is the easy case. So therefore, we can assume that the optimum just keeps its heavy server at one location for the entire duration of the phase. Now, if that one location is among the set of locations that we figured out over here, the costly locations, then look at the part of this phase where the algorithm has its heavy server at the same location. Okay, so during this part, both the adversary and the optimum and the algorithm is going to serve requests to the green page with the heavy server, right? And both of them are going to serve all of the requests using the light server. And therefore, If the algorithm pays W2 in this part, the optimum must also pay W2 during this part. Okay, so this is the other easy case. The slightly harder case is where the optimum keeps its heavy server at a location which is not in the set S, right? And in this case, we'll take help from the explore part, right? So let's just zoom into the explore part and see what happens. So the heavy server stays at this cyan location, and okay, so which means that it serves all the requests to the cyan location for free. It doesn't have to move any of its servers. Okay, but how many requests to the cyan? How many? What is the cost of all these requests, right? So we chose S to be the set of D most costly points, right? So and this cyan point is not in S, so therefore the cost that we save by keeping our heavy server at this point is at most 1 over D times W2. Okay, what else are we able to save? Let's just focus on the two requests that surround a cyan request. Okay, if they are the same color, which is the case everywhere over here, but in general it need not be the case, right? So if they are the same color, then by keeping the heavy server on the cyan request, the optimum is also saving on the cost of serving the next request. Why? Because when the optimum serves the previous request, right, it has its lighter server at the same point. Okay, but then how much is this saving? This saving is another 1 over D times W2. That's it, right? So except for these two savings, the adversary must move its lighter server whenever the algorithm moves its lighter server, right? So therefore, the net therefore the optimum definitely pays, even in this case the optimum definitely pays at least 1 minus 2 over D times W2. Okay. So now with this, the competitive analysis is relatively simple. In every phase, the algorithm pays at most 2D plus 1 times W2. The optimum pays at least 1 minus 2 over D times W2. Therefore, the competitive ratio is at most 2D plus 1 over 1 minus 2 over D. I hope I have done the math right over here. If you try to optimize over D, you will get that this is 18 competitive for D equal to 4. This apparently is the best choice of D under this setup. But the takeaway from all this discussion is the following, right? So we absolutely need our D to be greater than 2. Otherwise, this bound doesn't make sense. Optimum greater than 1 minus 2 over D times W2 doesn't make sense. But then for a generic value of D, the competitive ratio that we achieve is like theta of D. Okay. So now, how do we randomize it? Before we see the randomized version of this algorithm, let's take the second detour. Okay, so here is the other interesting problem that I wanted to talk about. It's called the online hiring problem. So let's say we have a set of candidates for certain position, right, in our office, and we interview them in a uniformly random order. The constraint is that as soon as we interview a candidate, we either have to give them an offer or reject them, right? We cannot come back to a candidate and say, look, you have the offer and so on. No, that's not allowed. What we want is, we definitely want to hire the best candidate, no matter what. Okay, but subject to this constraint, we would rather try to minimize the number of candidates we hire. Okay, so because we absolutely want the best candidate, what do we do, right? So here, when the first candidate came, the blue candidate came, potentially this person could be the best one, so we have to hire them, right? Next, the cyan person came, so the length of the segment basically indicates how good the candidate is. Think of it that way, right? So then the next cyan person came. It was this person was better than the first one, could possibly be the best one out of the lot. So therefore, we have to hire, right? If we get a person who is not the best among everybody who has come before that person, then we don't have to hire them, right? And so on. So every time we get a person who is better than all the previous, every time we get a candidate who's better than all the previous candidates, we hire them. Okay. So what is the expected number of candidates hired? Well, it's a rather straightforward calculation. So let's ask the question, what is the probability that it doesn't seem to be working? Acha. So let's ask the question, what is the probability that the ith candidate is hired? Well, if we condition on the set of the first I candidates that arrive, well, they arrive in a uniformly random order. So the probability that the best one out of that set arrives in the ith position is 1 over I. And that's exactly when we'll hire the ith candidate. So therefore, the probability that we hire the ith candidate is 1 over I. And then by linearity of expectation, the number of candidates hired is going to be 1 over 1 plus 1 over 2, blah, 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 up to 1 over n. N is the number of candidates. And this is the nth harmonic number. I think we saw this in the yesterday's talk. So this number is roughly the natural log of n. Okay. So now where does the hiring problem come into our setup on the weighted K server, weighted 2 servers algorithm design, right? So the randomized algorithm behaves as follows, right? So again, this randomized algorithm will also break the request sequence into phases. The definition of phase is slightly different this time. Just like before, the phase is going to be composed of the so-called explorer part and the exploit part. The algorithm's behavior on the explorer part is exactly the same as before, right? Just pretend as if the heavy server does not exist. Serve everything using the lighter server until you pay a cost, total cost, which is equal to the weight of the heavy server. Okay. Right. Next step is also the same. We just pick the top D, the D most costly requests in the Explorer part. Right. So here I have taken a D equal to 5 just to kind of make my point clear what is happening. Right. So the top D requests in this case turn out to be red, green, blue, cyan, and magenta. Right. And now things start to change. Now what we'll do is let's first see how we define the phase, and then we'll see how the algorithm works. Right. So how do we define the phase? Right. So we define it as follows. Let's just do the following. For every point in S, let's simulate. Right. Let's send the heavy server to that one point. Okay. And let's serve all the requests to points other than that one point using the light server until we pay a total cost of W2. Right. So we have started 5 simulations. In this blue simulation, we have sent the heavy server. For example, in this blue simulation, we have sent the heavy server to the blue point, and we are serving all the requests to points which are other than the blue point using the light server. And we are doing this until the total cost paid is W2, after which the simulation dies. Yeah. How are we simulating? We are not simulating the arrivals. This is analysis. Think of this as the analysis part. Right? I am yet to state the algorithm. I have not come to the algorithm. I'm just trying to define what is a phase in this case. Okay. So let's think of it right now. It's okay to think of the following. Right? We have the entire request sequence in advance. Right? We have constructed this set S, and we are just trying to figure out what is the end of the phase. Okay. So right. So these simulations die over time, and once the last simulation dies, that is what we define to be the end of the phase. Yeah. All right. Yeah, so this defines the phase. Now the plan is to prove that in every phase the algorithm, the optimum pays at least W2 roughly. In every phase the algorithm pays at most something times W2, and that will give us, that something will be the competitive ratio. So now what does the algorithm do? Right. So algorithm, right. So yeah, okay. So before we go to the algorithm, I want you to observe that the adversary must just by exactly the same argument as before, the adversary must pay at least 1 minus 2 over D times W2, right? Exactly the same argument as before. If the adversary moves the heavy server, it pays W2. If it keeps the heavy server at one of these 5 points, it pays W2, definitely by the same argument. Otherwise, something nice happens in the explore part. Okay. So now, how does the algorithm behave? Well, explorer part is exactly as before. The set S is chosen exactly as before. No change over here. Obviously, the algorithm has something to do with those simulations, right? So what the algorithm does is it, in its imagination, starts these 5 simulations, right? What does it do in its imagination? Whenever it gets a request, it just passes on that request to all the surviving simulations and and observes what each one of those does, right? But then the algorithm also has to actually serve the request in reality, right? So what I have done over here is I have randomly permuted the set S and put it down over here in a uniformly random order. Now the algorithm just picks one of those simulations, let's say the first one, right, and just follows exactly what that one simulation is doing until that simulation dies. Okay, once that simulation dies, it tries the next surviving simulation, which means what? It changes its configuration to the current configuration. Okay. So there's nothing wrong with this zoom lag. Oh, zoom lag. This is a lot of lag. Should I just use a keyboard? Won't help. Won't help. Wow. Yeah, okay, sure, please. Yeah, so the phase dies when you have paid a cost of W2, right? So obviously, since your heavy server is at that blue location, you're not paying for the request to the heavy to the blue location. Except for that, you are paying for all the requests, right? So when you have like W2 by W1 of those requests, except for the repetitions, that's when you die. Okay. Are we sure this is working? Okay, now it's here. All right. So now once one of the simulation dies, we move to the current configuration of the next simulation, which means we shift the heavy server to the cyan point and then continue that simulation until it dies, and so on, right? So this is exactly what we do. Every time our current simulation dies, we move to the next surviving simulation, and then once the last surviving simulation dies, we know that we are at the end of the phase. Okay. So how much have we paid in this process, right? So in this process, we have paid the cost of W2 in the explore part, plus every time we take a jump, every time we start a new simulation, we pay W2 for shifting the heavy server. And while we are following that one simulation, we pay at most W2, right? So for example, if you look at this science simulation, we have paid whatever the science simulation paid during this interval, which is, and in general, it's going to be less than or equal to W2. But conservatively, let's just assume we paid W2, right? So our total payment is going to be this W2 for the explore part plus the number of jumps times 2 times W2. But then what is the expected number of jumps? By the hiring problem argument, the expected number of jumps is exactly the expected number of candidates you would have hired if this was really the input to your hiring problem, right? So which is like the natural log of D. Okay, so now let's look at the competitive analysis once again. The algorithm's cost is like 2 times natural log of D plus 1 times W2. Optimum cost is exactly the same as before, 1 minus 2 over D times W2. The ratio of these two things becomes an upper bound on the competitive ratio. And the bound improves, right? So the takeaway over here is provided D is greater than 2 once again. So there is a lower bound, absolute lower bound on D, right? D less than 2, less than or equal to 2 is not going to work at all. So provided D greater than 2, our bound is like order of log D. Any questions so far? Here, we'll have to figure out what is the minimizer of this quantity. I'm not sure whether D is equal to 3 is the minimizer. Probably it is. I'm not sure. We'll have to check. But we are anyway not interested in the 2 server problem, right? So these are just, this is more like a building block for the K server problem, weighted K server problem, right? In that case, we'll have to choose a different D. We'll see that. Right? So now what do we do about the weighted K server problem? Right? The idea is more or less the same, right? The idea is to use whatever we have seen so far in a recursive manner. Okay, so again, your request sequence is going to be divided into phases. I'll define how, right? Every phase will have an explore part, have an exploit part, just like before, right? So what we do is we serve an initial segment of this request sequence using the cheapest K minus 1 servers, right? Now we pretend that the heaviest server does not exist. We just have K minus 1 servers. Recursively apply the algorithm, serve an initial segment until what? Until, if you just try to extrapolate from what we discussed before, the endpoint should be where we pay a total cost of WK, the cost of the heaviest server. But that's a bit tricky. Why? Because this recursive run is a randomized algorithm, and therefore the cost is a random variable, right? So if we define the end of this explore part to be the point where you pay total cost of WK, the location of this endpoint itself will become a random variable. And that makes the analysis completely messy, right? So we try to avoid it. We try to avoid it by designing an appropriate proxy for the cost, right? And this proxy is a deterministic quantity. It's completely a function of the request sequence. It has nothing to do with the random outcomes that that you encounter while running the algorithm recursively, right? So therefore, this end of the explore part is completely a function of the request sequence, right? There's nothing random in it. Now, when the explore part ends, we pick up again, if we go by what we did earlier, we'll have to pick up the D costliest points in our set S. But again, the cost that we incur on any given point, because this recursive part is a randomized algorithm, the cost is a random variable. Again, we want to avoid it. So therefore, we have to design an appropriate deterministic proxy for the cost, right? So the deterministic proxy for this, to decide the end of the explore part, the deterministic proxy for deciding the cost, the payment made for each point, are really the contributions, the real contributions which basically led into this algorithm. Everything else is kind of easy. Right, so this S is chosen to be the set of D maximizers of the proxy cost, the deterministic proxy cost. Okay, then the idea is again the same, right? So you start so many simulations in parallel, you follow one of them until once again its deterministic proxy cost hits WK. Okay, and then you switch to the next one, exactly as before. Right, remember these are arranged from top to bottom in a uniformly random order over the set S, and yeah, that's it. Yeah. What is the jump? So basically this simulation has ended. This simulation is running at some configuration. You change your configuration from whatever you were at to the current configuration of the next simulation, right? So for that to work, you'll have to assume that the weights are kind of exponentially separated, which is without loss of generality. And then the amount you pay in the switch is like some constant times WK. What doesn't become 2 to the power 5?
Yeah, D5. It's not that the number of possible jumps are 2 power 5. That doesn't happen.
No. The number of possible jumps is log of the size of S in any case. Right? The number of
configurations to be switched
are
not exploding as 2 power 5.
No, not at all, right? So we are, whatever random configuration this simulation is at, we'll move to that one thing.
So
blue one is moved to the cyan one, yeah.
Other K minus 1, which will recursively also have to.
No, everything happens in one shot, right?
How possible changes happen?
At most K, right? So think of this as a randomized algorithm, right? So therefore the configuration it has over here is just one sample out of whatever distribution it is. You just move to that one sample. No, not at all. Yeah. Okay, so now obviously I will not be able to present all the details of the analysis. I'll just give a sketch of what is happening in this case. Again, it's not going ahead. Oh, okay, yeah. So just like we had, what did we have earlier, right? We absolutely needed our D to be at least 3 for the analysis to work. And then depending on the value of D, we had some competitive bound. In this case, when we work it out, we actually need our D to be like doubly exponential in K for all the analysis to work out. Okay. How does the competitive ratio behave? Okay. So in this case, in the earlier case, we saw that we lost this 1 minus 2 over D factor, right? When we analyze the optimum. In this case, we lose a full 2 to the power K factor in our analysis, right? So optimum, it's possible to prove that the optimum pays at least WK by 2 to the power K in every phase. While what happens to the algorithm's payment? Well, the algorithm's payment roughly is order log D is the number of switches, number of jumps you make in the exploit part. Every time you make a jump, you pay some constant times wk. Well, I've missed out this constant over here because you'll have to possibly change your entire configuration to the new one, not just the heavy server. And then so every time you do this, you are giving a recursive call, right, to the k-1 server algorithm, right? So whatever is the cost of the expected cost of the recursive call, that's what you'll have to pay over here. And because this okay, so if we imagine that the cost that we pay, expected cost that we pay is like some ck, some constant ck times wk, the weight of the heaviest server, what we get as ck-wk is like 1 plus order log d time. So this 1 times wk is the cost for the explore part, order log d, sorry, I think I've messed up the parentheses over here. The point is we are running this recursive calls, right? And for each recursive call, you are paying an expected cost of ck minus 1 times wk, right? And if you just try to solve this recurrence, what you'll get is, yeah. So what you'll get is this ck is going to be like log d to the power k, right? Because these ci's will multiply if you try to solve this recurrence. And since you're forced to pick your d to be doubly exponential in k, log d is going to be exponential in k. Exponential in k to the power k is going to be exponential in k square. Okay, so I'll just conclude this talk with a few open problems. I think I mentioned some of these yesterday itself, right? So the first open problem is try to close the gap between the lower bound, which is exponential in k, upper bound, which is exponential in k squared. I have zero ideas how you could do this. Yeah.
For this particular algorithm, is that tight?
For this particular algorithm, is the exponential k squared tight? I actually don't know. We'll have to look into it because I can't imagine you'll get anything substantially better than the bound, but we have been careless about analysis. Let me just admit that, right? We have like been careless about the constant factors and so on. So it's, yeah. So there is a gap which needs to be closed. This is a challenge problem that I mentioned in yesterday's talk, which is try to solve the weighted k server on general metrics. Well, that is too ambitious. The simplest case, in my opinion, is going to be the following. Obviously, k equal to 3, and we should target some very simple metrics which are different from uniform metrics, right? How different from uniform metrics? Obviously, we don't want a metric in which the maximum distance to the minimum distance is like at most 100. If we restrict our attention to these kind of metrics, what we could do is just pretend as if those are uniform metrics, give up that 100 factor in the competitive ratio and get done with it. No, we want metric spaces. We want a class of metric spaces in which you have metrics with arbitrary, what is called, it's called aspect ratio, right? Metrics with arbitrary separation between the largest and the smallest distance. So what is the simplest such class of metrics? Well, in my opinion, I would recommend you to try the following, right? So let's say we have the tree with 3 layers, right? The set of leaves is the set of points in the metric space. Now, if the distance between any 2 points is basically the label of their lowest common ancestor, right? So if 2 points belong to the same subtree, they are a distance 1 apart. If they belong to 2 different subtrees, they are a distance L apart, and L is some constant which is arbitrarily large as compared to 1, right? So k equal to 3, try to get a competitive algorithm for this metric space. Okay. So the one thing I also want to try out is the following, right? So if we just look into our the exponential k squared algorithm, it's running recursively, number one, in every and in it's simulating lots of things, right? So it's taking this d to be doubly exponential. It's simulating those doubly exponentially many copies of the algorithm for k-1 servers, and those copies are in turn running their own simulations, right? So if you just do the calculation, we are using an enormous amount of space, right? Obviously, we are using an enormous amount of time also to decide what do we do, how do we serve the next request. Can we try to understand some kind of a trade-off between the competitive ratio and the usual computational complexity parameters like space and time? Yeah. So can we get an algorithm which is still, let's say, exponential in k squared or something, or exponential in k, hopefully, but which uses much less memory than what we are using? Yeah. So that's the open problem I would like to stop with. Yeah.
Okay, exponential in k.
Yeah.
It does not make sense to go back and look back at the Markov page.
Sure. Markov paging, as in the request sequence, come from some kind of a Markov chain.
Because there,
Hmm.
the unweighted case
Mm-hmm.
was an optimal.
That is actually an interesting question, right? So if I just slightly simplify it and say, okay, every request is drawn independently from the same fixed distribution, then that's an easy solution. That has an easy solution. What do? You just pick the k minus one most probable requests, keep your all your k minus one servers except the lightest one at those points, and serve all the other requests using the lightest server. That, I guess, would be the best you can do if your requests are coming in an IID manner, right? Are drawn independently and identically distributed manner. But what Rahul is saying is, what if they come from some kind of a Markov chain? We'll have to think.
So leave for unweighted case, the algorithm highly not the optimal algorithm.
Mm-hmm.
The one you suggested doesn't actually work.
You mean unweighted case? Sorry.
Yeah, in the unweighted case.
What doesn't work?
In the Markov setting,
the
algorithm you just suggested actually does not have those things how your
Acha, I see.
it's far too complicated even in the unweighted case.
Mm-hmm.
Even that with the thing of exponential in k.
Yeah, definitely.
Some restriction has to be put on there.
Yeah. Sure. So if you consider the practical setting, what I completely agree with you. Yeah. I mean, basically, I'm more intrigued by this problem of whether there even exists a competitive algorithm for k equal to 3. Some constant competitive algorithm for k equal to 3. This kind of a metric, yeah, k equal to 3, no algorithm is known for this kind of a metric. And by the way, this is not really a tree metric. A tree metric means, okay, you'll have to sum up the weights of the edges on the path. Mm-hmm. 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 Yeah. I get it. Basically, in the Explorer part, you're paying a cost W2 using the light server. Then you're moving the heavy server, paying W2 with it, and so on. You're kind of alternating between the two. I get your point. Yes. Yeah, valid point. What balance algorithm exactly now?
So both the servers essentially going to be as close in terms of their power.
Mm-hmm.
That's what the balance is. So
I see.
the cheaper one first. Now it has hit W2.
I doubt whether that will work, because as soon as I know you're going to move the heavy server, I'll make sure that you're going to move it at some irrelevant point. Yeah.
So what are the stochastic models that people have studied under IIT? And there's also
Markov, as you mentioned. Actually, I have not actually explored too much into that area. All I can imagine is some kind of Markov chain. Yeah.
Not minimize the hitting time. It's that hitting time I will not pick off it. Markov setting. It's an application. Would like to solve it. But for that, actually, optimal algorithm is what's that? Yeah, nice enough structure, but it's not straightforward. So beautiful paper, this is called Markov. All right, the no more question. Let's thank Ashish. Let's not get free.